All right, so looks like I wanna show you one thing about the graphing. If I start typing graphing calculator, Desmos. So it's a free graphing calculator. I think we already used it once or so. And reason I wanna do this is to check out some of the, well, obviously graphing things. And I saw a number of exercises here that would like you to graph the parametric equations using the tool, because otherwise it may be a little bit tricky. So if I see how we could use this graphing calculator, so say 4t over 1 plus t cubed. So I will go back to graphing and put, I think I need to maybe go parametric equations graphing. So in Desmos. So it gives you example. So the parameter is restricted and equations with a comma that you could produce as your graphs. So if I try it, one here, first is 2t 1 plus t cubed. T, just enter 2t divided. So I need to get this keyboard by 1 plus t cubed. At this point, you don't want to look at the picture because it's not what it's needed. It's just little by little come into the part we need to look at. And then the second equation, and please notice it doesn't really matter because calculator does not care what you're entering. Little by little, it will graph it for you. And the other is 4t squared over 1 plus t cubed. Okay. Or t squared that I divide by 1 plus t cubed. I decided to show you the graphing abilities because I think it's a great tool that they provided you for absolutely free. Now, parameter t, notice is this case, it's not minus to 5, minus 5 to plus 5. It is definitely something else. So what they want me to actually graph in here, so I can check it out. Is there any restriction they have? And they want an interval of 0 to 1. Okay, so you can change the limits from 0 to 1. So please notice that's nice to have a free tool such as a graphing calculator available. And again, all you need is to graph, to go for the Google search, put parametric graphing calculator or something like that, and Desmos will do it for you. So the message is whenever they ask you to graph something, well, use graphing calculator because otherwise it will take you forever. In fact, with the exercises of this kind, it will take you really a long time to get the ideas of the graph because this function is far from obvious. And the same with all the others. So advice is use a free tool to get everything graphed. Looks like lots of exercises that expect you to do that, and then answer all kinds of related questions. So I want to talk a little bit more about chapter 10. And before, I want to say that I received already some exams and I was very impressed. Very good job. So perfect. And I will be placing grades tomorrow because today is a due day. So I'll wait for more people to submit their final exam as well as homework. So there are two pieces. One email should have a final, the other should have homework. And after you send it to me, I will, of course, respond. Thank you for sending me your work, and I will grade it and I will post grades on the Brightspace. So again, the plan is to do it tomorrow. So on Thursday, which is our very last class meeting, I will be, of course, here again on Zoom as usual, and we can discuss grade if you like, usually to increase it, right? And to raise the grade, all you need is make sure you submitted the exam and then you submitted your homework. So if you don't submit homework, it'd be a little lower the grade. So just I will tell you, email me whatever you have done. And what you need is just basically copy one exercise from every lecture we had since midterm. So that's probably like 10, 11 lectures, something like that. So the 10 problems, you can just copy them. Or you can do something on your own if you like, but doesn't matter to me. As long as you try good, you will get full credit. But make sure you email me your homework. So that's important. So anyways, I want to say polar coordinate story, a little bit of that story, that deals with graphing all those circular produced graphs. So if you have something that is designed, well, like circle or various trig graphs, like one they have here, then you can use polar coordinates for nicer description. So polar coordinates, I'm sure you saw this already in trig classes, so I will not be too long with that, but the point of story that's not x and y axis. Your polar coordinates are totally different. One is radius and the other is theta. So for example, if you have a point, so there is a pole, that's where polar coordinates being produced, and the positive direction of polar axis. When I say that's x-axis, no, that's polar axis. It's totally different. That's the idea. You can relate x and y coordinates with polar coordinates, but it's totally different description. For example, if you have a point on the polar plane, then you can definitely connect it with a pole. And then you see the distance from the pole to that point. We call it as r. And then we also have the angle theta. So the point, each point on the polar plane is given as a pair, radius r and angle theta. And it overlaps. Compared to xy plane, it's a little different because, for example, if you try the other point, well, actually, let's say same point, r theta, me just give an example. So let me get r equal to pi over 4 angle and theta, sorry, I need to wake up. Yes, theta is pi over 4, and then radius r is equal to 2, for example. So if you try to make a picture of that point, then you, of course, gonna get the distance 2, but first you put angle measured pi over 4. So 45 degrees angle, and so angle is pi over 4 and 2 for r. But you could describe it differently. You know that. For example, you could rotate clockwise and end up in the same place. So you can rotate by negative. How many pi's over 4 we take here? Well, looks like it's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8? No, 7. 7 pi over 4. And radius is still 2. So that'd be exactly the same point on the plane. If you rotate, not counterclockwise by pi over 4, but you start always here at the pole, so you rotate clockwise by negative 7 pi over 4, you're going to end up in the same direction. Or you could also do it differently. The third way to produce it is instead of r to use negative 2. So if I imagine myself if I go pi over 4 and then negative 2, then I will go here. But to actually return back, I need to go extra half rotation. So that will be not 1 pi over 4, but 5. Because if I go 1, 2, 3, 4, 5 powers over 4, it'll be on that ray. But if my radius is not positive 2, but negative, I'll have to reflect it the opposite direction. You see, these points are all the same. In fact, there are infinitely many of them because you could go with positive 2 and then go full period plus, so plus pi over 4 plus 2 pi or plus 4 pi or plus 6 pi, any even number of pi's. Or you could go the negative direction, just like we did here. Or you could go with a pi over 4 and then negative radius. So that way we get different looking representations of exactly the same point. So the polar plane, they say, overlaps with itself infinitely many times, basically. That's worth to think about. That's why polar coordinates, they're good, but they have multiple results. That works pretty well for functions such as sines, cosines. They also have period 2 pi. So eventually, if you decide to take complex variable functions course, you will encounter those overlapping planes. But anyways, this is what we have for polar coordinates. And the amazing fact about them is that those regular XY coordinates that we are used to deal with, or Cartesian or Descartes coordinates, were known by Descartes. He introduces them, they say, about 400 years ago or so. So what coordinates people used prior to Descartes? Well, who knows? Maybe those were polar coordinates. So that's something to think about. But anyways, the conversion. So you can write points in terms of XY coordinates or in terms of r and theta coordinates. So if you look at any point on the plane, then you can describe this point with respect to r and theta. And of course, if you look at this right triangle, then the definition of cosine will be x coordinate and sine y coordinates times radius r, right? Because if it's a unit circle, it's just one, but if it's whatever r is in general, then times radius r. And then you can also convert them back from Descartes xy coordinates to theta and r, so to polar coordinates, using the fact that if you again look at this right triangle, the tangent is same as if you divided the opposite side by the adjacent side, right? So if you divide opposite over adjacent, that's a definition of tangent. If you have a right triangle, 90-degree angle, and that's exactly y over x. So you can have expression for angle from those coordinates, as well as the Pythagorean theorem again, since it's right triangle, hypotenuse is r, so r squared is sum of squares of x and y. So you can produce expressions for theta and for r. So you can convert back and forth for convenience. And of course, most graphs are convenient to graph using XY coordinates. I say, Alex, everything is nice and convenient. Well, in trigonometry for trig functions, turns out it's more convenient to graph using the polar coordinates. So if we can check out some of the graphs, here's the graphs. I guess that's nice. So if you look at the r equal to 2, for example, well, r is equal to 2 means there is no theta. So theta is anything, any angle. And it means you can go on the radius 2 distance, and then this point will be with coordinates radius 2 angle is 0, and that point will be with coordinates radius 2 and the angle is pi over 2. So it looks like any angle from 0 to 2 pi will have representation on this circle, and that's the picture. And of course, if I just say any real, it will mean that we can just rotate it as many times as we want. So usually people say the theta is in between 0 and 2 pi. So you don't consider the cases of infinitely many overlaps, and they include 0 here. So this way we have unique representation. And again, r is always positive, because technically in the polar coordinates, r could be negative. So it's a negative distance. Well, the opposite direction, that's for negative. So Higgs equation for circle, just radius is equal to 2. It's much simpler than the one that we used to get, like x squared plus y squared. Says too much, right? So point of story, when you have circular type of equations, it's more convenient to use those polar coordinates. So if you look at the other case, r is equal to secant, and secant is 1 over cosine of theta. Then I can multiply by cosine of theta both sides and see that this is x. You see, why is that? Well, because definition of conversion of x and y. So x is r cosine. We just had it on the previous page, but I'm sure one could forget that right away. And y is r sine. So those two formulas one needs to keep in mind when working with polar coordinates. And you can actually see those formulas in the upper page. I will scroll it up soon, but the point of story that I just produced equation x equal to 1, which means that we have a graph of a vertical line that passes through 1. So sometimes it is better, I think, to graph with our favorite xy coordinates, and sometimes when something is circular, it's more convenient to graph with those new polar coordinates. So they actually have it here. So, same thing. So anyways, there's a graph. So for the regular graphing in terms of polar coordinates, turns out they usually utilize some trig functions. So let me get some room here. Right, so just clean a little bit. So if you have the graph here with polar coordinates, r is equal to cosine of 3 theta, it turns out the process is pretty standard. In order to graph, you need to know 3 things. So when r and corresponding angle theta to it. So r equal to 0, r is equal to maximum, and r is equal to minimum. So that's standard we used in trig classes. So I need to find the corresponding angles. But first I need to see what's going to be the maximum possible value for radius. In other words, what values cosine function can take on. And it is always varying between plus and minus 1, right? So it looks like minimum will be done -2 and positive will be +2. Why is that? Well, because the lowest is -1, the minimum for the cosine. So your function for radius is 2 times cosine. So it's 2 times -1. So it's -2. And analogous for maximum. Maximum is +1. So maximum cosine is going to be 1, and it's just multiplied by 2. And that's 2. We say, why is it multiplied by 2? Well, because that's what we're graphing. They gave us this. So, well, trying to always find these 3 values. And looks like minimum and maximum going to happen when we have our angles theta in particular values. So, for example, when cosine of 3 thetas is equal to 1, then our point on the unit circle that corresponds to cosine is x coordinate, which is 0 and so forth, multiple of 2 pi, right? So people say 2 pi k or 2 pi n, whatever you like. N is set of all real numbers. So theta then will be 2 pi or 3 times. So for various values of n, and n is any integer, or people like to call it with set z. So we utilize such values as 0. So when n is 0, then theta is going to be 2 pi times 0 pi over 3 times 0. When it is 1, so I take 0, 1, 2, and so forth. So there are multiples of pi, 2 pi over 3. So if I think about the unit circle, then it's going to be an angle measured 0 or 2 pi over 3, which is 120 degrees, and then 4 pi over 3. 4 pi over 3, which is going to be let me put them on the unit circle so you will see that that's all we need. 0 here. So 2 pi over 3. This is 0. And then that's 4 pi over 3 here. So if you keep rotating them, they're gonna keep repeating again and again. That's why those are 3 points on the unit circle I care about. And what about -2 values? Well, again, I'm dealing with this function, so cosine of 3 theta is -1. So when is it -1? Well, maybe let me use another color. Red. So that will be here, cosine -1. So it's cosine of pi. You say negative pi. Yeah, multiples of negative 2 pi, multiples of, there's a pi plus multiples of 2 pi or minus multiple of 2 pi. So again, I divide this by 3, I'm sorry, sometimes I throat. So it looks like then what I start with here is solving, this is -1. So what's going to be values of radius? Well, looks like analogous to these guys. I'm going to have that one, and that one. Right? So you can see that bunch of these 2 pi's over 3, but it's actually right. So anyways, another trick procedure in here, and notice that now we can describe all of these points by taking pi over 3 and adding, subtracting, but the radius will be different. And finally, when r is equal to 0. So r is equal to 0, add, now I use another color here or there. When you say, Alex, why r is 0? Well, because cosine of angle is x coordinate. So for that angle, pi over 2, or for minus pi over 2, we have x coordinate. So how can I describe those? Well, let me write it maybe here. So cosine of 3 thetas is going to be equal to pi over 2 plus pi times n. So I can write pi over 2 plus pi times n. So now I need to pull out my thetas, and I'll divide by 3, so that'd be divided by 3. I put extra 3 in denominator, so it will be pi over 6 plus pi over 3 times n. Which means that first angle is going to be pi over 6 and then I can add another 2 pi over 6, so that'd be 3 pi over 6. Is it that same as pi over 2? Yes. And then add another 2 pi over 6, so that'd be 5 pi over 6. And so forth. So it looks like angle theta is running through a bunch of values. Pi over 6, then 2, so pi over 2, and then 5 pi over 6, and so forth. So just add another multiple of pi over 6 twice. So that'd be 7 pi over 6, and 6 values. 9 pi over 6, which is just pi, and so forth. Let's see how many of them, 6 of them. So you can add another 2. That is that pi, 7, 9 pi over 6, it's actually 3 pi over 2. Sorry. Okay. Pi over 2. Okay, just add 2 more. 9, so plus 2 is going to be 11, right? 11 pi over 6, and finally 13. Just list all of them. Okay, so those going to be points. Probably should not have this big picture here. So those points are the ones that will be poles or 0.00. So why do I need them? Well, let's start with maximums. So maximum is when angle theta is 0. So that's going to be 2 for radius and 0 for angle. They actually have it here. And then another maximum will be when we have angle of 2 pi over 3. So that'd be the one in here. And then another maximum will be the one is there. Okay, so what happens now, the way the graphs they show goes somehow like that. So what's happening here? Well, the angle from being 0 now goes to pi over 6. Right, it starts on increasing from 0 to pi over 6. So when we have pi over 6, we go to the pole. So we start at this point, and our angles increase, but distance to the pole R decrease, and eventually it becomes 0. And then the next portion goes towards radius R equal to -2. So when R is equal to -2, we have the opposite pieces to take. So let me use another color. Maybe I'll use yellow. So the graph would probably go like that pedal, and then return back again to the next pole position somewhere at 2 pi over 3, no, at pi over 2, 90 degrees angle. But it's actually going to be a negative values of radius. And when radius is negative, then the points need to be reflected. So they're actually going to go like that. Well, I meant it's 2, so it's also 2, hopefully, but let's say it's not 2, should have been further to the right. But the point of observing now, this pedal is reflected here because, again, R is going towards negative. So that happens when R is -2. So the theta values are going to be such as where the -2 values are. Pi over 3, then next is going to be pi over 2. So towards 90 degrees angle. So when theta increases, but the point's reflected through the center. See how it comes out. And then we go to the third quadrant, and again, the R will be positive, so it will actually produce a picture that we need, and it's drawn right here, you see. And one can say, Alex, so looks like your ending picture is here. Yes, but the problem is that it double covers itself. So the next piece is going to be drawn again like that. And then the piece that needs to be attached to it in this area will be reflected to there. So instead of being with positive angles, because are now going to be negatives, they're going to reflect to this one. And then the process will repeat. So now the next pedal will actually cover itself because R is positive. So it's going to be double drawn, this whole so-called rose, the 3-petal rose. I hope you saw this before in trigonometry. If not, it's worth to think about how it's being graphed. And I definitely don't think that this is the good example to do first when nobody saw how to graph in polar coordinates before, but I know that you had trigonometry as prerequisite for this class, and that's where we spend the whole chapter is about all the graphing. So that's why my goal was just to refresh your memories. But one can say, if I never saw this before, if we skip it when I took trigonometry or forgot, well, then maybe you can refresh your memories or use graphing calculator. And I think this is an excellent example. They also work it out. But the point is you need to get those R equal to 0, the so-called poles, because at the poles, one amazing thing happens. At the poles, the tangent line to the graph enables me to actually get a graph such that it touches my picture at the pole, the tangent line. So, and that's where I guess the last thing I wanted to discuss today, an interesting theorem is coming from, so maybe I'm gonna clean my mess in here. I'm gonna stop share and then share this again. And the theorem says that tangent lines at the pole. So it helps to graph. So because one can say, so why is that going to be a tangent line? Because turns out because of theorem 10.12. So if that's a pole, then the line with equation angle alpha, so angle theta is same as that particular value, is going to be tangent at the pole. So that's why if it's a tangent line, so now that's tangent line, your function should be going such a way that the line will be tangent exactly at that pole point 0. And that's actually why we can graph like that. And that's what we utilized in trigonometry classes for granted, basically, because to get to this theorem, we need to know calculus, we need to know the definition of derivatives. So the point of this theorem is if you have dy over dx, and last time I guess I dx as dy over d theta. Remember last time we had in parametric coordinates the definition of derivative. So if your parameter is angle theta, I say, why is it angle theta? Well, because in our case, when you are working with x coordinate, which is r times cosine theta, and y, which is r times sine of theta. So this pair of formulas I already wrote today, and we actually heavily use them here. So if r is also some function of theta, that's the polar equation. So I will replace this with function of theta. So it will be multiplied by cosine of theta. That's my x. And my y is also going to be replacing r with some function of theta. And it's multiplied by the sine of theta. So those are my polar coordinates in parametric form. Then when I decide to take dy d theta, this is derivative of product. And notice that derivative of product is going to be first times second plus second times first. So they have here second times first, f prime times sine. That's actually first derivative of first times second, and then plus, and then derivative of sine is cosine times f of cosine, f of theta. So that's derivative of numerator, which is a product. And analogously for denominator, we have to take derivative of dx d theta. So I differentiate again a product of two functions of theta here. So derivative of the function f times cosine. And then derivative of cosine is negative sine, so that'd be minus sine times f of a. And notice then since f of a, f of alpha is going to be a pole point, so the f of alpha is going to be 0 here and here. So those terms will disappear. And then when you have a fraction here, derivatives cancel each other, you end up with sine over cosine, which is tangent. So our derivative at the pole is tangent. So the tangent line at the pole, so it touches the graph. And that's justification of this theorem, which is enabling us to get graphs. I think this is a good moment to stop for today, because I know that most of people in class are working on the final exam that has nothing to do with this story. Final exam I emailed, and I just also put it on Brightspace. So the final is on the Brightspace if you prefer to use it there, but please do it on the piece of paper and email it to me, because practice shows if you try to put it on the Brightspace, sometimes I cannot open it. So it's easier, instead of uploading it to Brightspace, just upload to your email, takes same as long, and send me email with your work on the final, as well as your homework. If you haven't done it yet, please do this, because today is the due day, so that way tomorrow I will collect all the information and put your grade on the Brightspace if I get it by that time. If not, I'll just leave it blank. So we'll wait till Thursday. So I give you this exam in advance so you have more time to think about it. So I guess if you have any questions related to the exam, please ask, or if you want to just write it in Zoom chat, you can put it in the chat. Or if you're already done with the exam, I already graded it and I said I liked work very good. So I'm not putting it yet in the Brightspace because the system designed such a way that I have to put them all at the same time. So that's why I'm waiting till tomorrow. So tomorrow, sometime in the afternoon, I will put grades on the Brightspace. So you will see what you got on the exam and then what your, again, predicted grade for the class is. Predicted because if I don't receive some of your work, then it'd be a little lower, but it can always be changed. So we'll discuss that on Thursday. So I'm gonna stop recording. Thank you for being here. And again, I'm waiting for your questions. Stop.